Welcome once again in a physics class. In today's class, we will try to do electric potential energy of an electric dipole in an electric field. This electric field is assumed to be what? Uniform electric field. So what we are going to learn today is what electric potential energy of an electric dipole when placed inside an external field of uniform 1. Okay, when placed inside what? An uniform electric field. Got it? Yes. Let an electric dipole AB, okay, AB is here. This is an electric dipole, okay, of length twice L. This length, dipole length is twice L, be placed inside an electric field, okay, inside an uniform electric field, capital E, such that the dipole moment P vector from negative charge to positive charge, okay, is making an angle theta with that of the electric field E. Got it? So you try to remember this diagram. When we go to the next slide, you will be difficult if you don't know this diagram. So try to remember this. Look it carefully here. Okay. Now in the next slide, we will try to find out what the small work done in rotating the dipole through small angle delta d theta. Okay, so you just remember this AB is an electric dipole of length twice L. O is the middle point of the dipole, and your dipole moment P vector is acting along from A to B, A being the negative charge, B being the positive charge. It will be from A to B, and this dipole moment makes an angle theta with the electric field E. So two charges. Okay, this uniform field can be assumed that one positive plate is somewhere here, another negative plate is somewhere here on the right side. So what happens? Electric field will be from this left side positive plate toward the negative right side plate. Okay, and it will be what? Uniform. So you just think it in that way. Then what happens? If it is positive plate, your negative charge will be attracted toward it. This is positive charge, so it will be attracted toward the negative. So you can think it in that way. Or rather, if you are placing inside the electric field E, so this negative charge will experience a force toward this direction. That means against the electric field E, but the positive charge will be experiencing a force QE along this direction of the field. You know, in the case of what? Electric field, how do we define electric field E? E is defined as what? Force per unit charge, right? Force divided by charge. So if you try to bring force per unit charge like this, then it is known as electric field E. So if you want to find out force, then it will be what? Q times E. So the force experienced by this Q will be equal to what? QE along the direction of the field, and the force experienced by this minus Q will be QE in the direction opposite to what? Electric field E. Now you try to drop perpendicular, okay, from this point B, okay, and you try to produce this parallel to the electric field at this point C. Then this will be a right triangle. Okay, ABC will be a right triangle, and this angle, what? This BAC is also having that angle theta. Now in finding this what? Potential energy, let's try to see what are the things that we need to find out. And actually we need to find a torque. Okay, torque, and torque is just similar to that of force in the case of linear motion. So force into distance, we call it that as work done, but in the rotational motion it will be torque into that small angular displacement theta. Okay, so let's see in the next slide what we can see. You just try to remember this figure. When I go to the next slide, then this figure will not be there, so you try to remember at the time. Okay, yes, then small work done in rotating the dipole through an angle d theta is what? Small amount of work done is denoted by dw. Why? Because angular displacement is also small, so your work done will be also small. So as I told you that work done is equal to force into distance in the case of linear motion, but in the case of rotational motion, instead of that linear force, it will be replaced by rotational force, what we call as torque. Instead of linear displacement ds or dr, it will be replaced by the small angular displacement d theta. Got it? So tau, that means torque, we know that that is equal to pe. Got it? Pe sine theta d theta. Pe sine theta, what is this P? Dipole moment. E is what? Electric field E, sine theta d theta. Why? Because your torque is expressed as P cross E. Tau is a vector quantity, torque is a vector quantity, your dipole moment is a vector quantity, E is a vector quantity. So this is a cross product of P and E. So P and E, angle between them, P and E is what? Theta. When you say cross product, then it will be equal to what? PE, this will be equal to PE sine of the smaller angle between what? This P and E. That is nothing, PE sine theta. That is what I'm writing here. So work done in rotating the dipole from theta 1 to theta 2. Theta 1 should be taken as 90 degree, theta 2 should be taken as theta. So in rotating an angle theta, how much work done would be? Okay, there we need to find it out. That amount of work done will be stored in the form of potential energy to that dipole inside the electric field. Got it? That is what the main aim that we are going to do. Now, work done in rotating, why we are taking this theta 1 is equal to 90 degree. There is a specific reason, valid reason for it. I will tell you later on. Okay. Now after this, so your total work done will be equal to integration of such small dw's for small angular displacement d theta. Okay, we can't take it the help of summation, rather the number is numerous, so we have to take the help of integration. So w is equal to integration of such dw's from where to where we need to integrate it, from theta 1 to theta 2. Okay, so you need to integrate this from theta 1 to theta 2. Pe being constant quantity, dipole moment, as long as you are not changing that dipole, your dipole moment will remain same. As long as you are not changing that external field, this E also constant, so you take this P and E outside the integration because they are constant. Got it? So integration of sine theta d theta, from where to where? Theta is equal to 90 degree to theta. Got it? And this will be equal to what? Integration of sine theta is minus cos theta, we all know it, that one. So what? PE minus cosine of theta from 90 degree to theta. Okay, so 90 degree is the what? Lower limit, theta is the upper limit. So you try to replace this upper limit by the upper limit first, this variable by the lower limit next. So if you do it like that, then cosine of 90 degree is 0, so we get it only PE cos of theta, like that only. And we can write it this as P minus of P vector dot E vector. So this is the resulting formula, okay, for finding that work done. So your potential energy, okay, will be also equal to this amount of work done. Why? Because this amount of work done will be stored in the form of potential energy onto that system. What system? System of that dipole inside that uniform electric field E. Okay. Now, why we are taking this lower limit as theta equal to 90 degree? Suppose if you want to find out that electric potential energy of a dipole, then we need to take it from where that work done is 0 as a reference point. Got it? So when theta is equal to 90 degree, then what happens? Your potential energy is 0, right? Suppose if you want to find out gravitational potential energy, you need to take that object from the surface of the ground where that potential energy is 0 to a certain height. Got it? Suppose if you are trying to find out that potential energy, you all know that gravitational potential energy, the formula is equal to mgh, right? So how do you find that potential energy? Suppose on the ground, if you are on the ground, then height of this object is how much? 0. So your potential energy here will be what? Potential energy mgh, this will be equal to 0. Suppose you want to find gravitational potential energy at this point. I'm talking not about electricity, okay? I'm talking about your class 11 gravitation. Now let's take the analogy, okay? The similarity, I mean. So on the surface of the earth, the object of mass m, its potential energy will be equal to 0, right? When you take that up to some certain height, h, say this height is denoted by h. So what happened? Your potential energy at that height will be equal to what? mgh, right? How do you find it? That mgh actually, that mgh is nothing but this is the amount of work done. Work should be done against that weight mg. Your w is equal to mg, right? And the distance is how much? Height h. So against this what force, you need to do work, and that work must be what? That force must be equal and opposite to this mg. So the force will be what? Mg. So if you want to find that work, then it will be force into distance. Got it? So likewise, you try to find out your potential energy there at the position above the surface of the earth at a height, say heights. Likewise, we started from here where the potential energy, okay, is equal to 0, where the work done is equal to 0. Likewise, from that work done equal to 0 up to some certain height, we need to take it here also from where the reference point should be, from their position of whose work done is 0. We need to take it from work done 0 to that position where we want to find the potential energy, right? Gravitational potential, I mean. So gravitational potential at this position of height h is equal to this. That is nothing but the difference of these two. From where we are taking the reference point, we are taking from the surface of the earth where the potential energy is 0. Likewise, from here also, potential energy 0 means work done is 0, okay? So we need to take it that reference from where the work done or potential energy is 0. That happens when this theta is equal to 90 degree. That means when your dipole moment is making an angle 90 degree with the electric field. Can you get the point? Yes, you got it. So what happened? Your potential energy, okay, this amount of work done will be stored, this amount of work done, that means this one will be stored in the form of potential energy, and your potential energy is denoted by what? By U. So your U will be equal to what? Minus of P dot E. Got it? Don't forget this formula. And mind you one thing, at the time of examination when you are asked to solve that numerical problem, don't use this formula first, okay? You better use that formula starting from 90 degree to theta, okay? Suppose if you are asked to find out the work done or potential energy stored from some one angle to another angle, okay? In that case, you need to take it this formula as the formula, okay? Suppose if you want to rotate an angle up to say some theta 60 degree, then if you are asked to find out the amount of potential energy or the amount of work done in rotating that dipole through an angle 60 degree, for example, then you should not use that formula, this formula directly, and don't put it that minus of cosine 60 degree there. Got it? Angle between them is 60 degree. Don't put it in that way. It will give you some certain mistake later on. So you better start it from this expression. Got it? Clear? From theta 1, you take it this as theta 1 and this as theta 2. So theta 1, you take it that as what? The given angle. and this as the another angle. Okay, so you better use it this formula first. So suppose if you are asked to find out the potential energy or the work done in rotating that dipole from theta 1 is equal to say 20 degree to 30 degree like that, then you better use this formula. Okay, from theta equal to what, 30 degree to 40 degree like that, if you are asked. Okay, so this will be the first theta, this will be the second theta. Okay, that means this will be the first lower limit, second what, upper limit, right? In that way you can take it. Got it? Now let's say some special cases. Okay, when theta, that means here if dot is not there, then it will be cosine of theta. Okay, when theta is equal to 0 degree, that means when your dipole moment and electric field E vector are parallel to each other, then what happens, your potential energy will be equal to what, minus PE, because cos of 0 degree is 1, and this is minimum potential energy. Got it? When theta is equal to 90 degree, that means when dipole moment or length of a dipole is perpendicular to the electric field E. Got it? Your dipole will be lying like this, electric field will be horizontal as in the diagram from left to right, and your dipole will be vertical here like this. Got it? In that case, what happened? Your potential energy is equal to 0, and we take this position as a reference position. Okay, when theta is equal to 180 degree, that means no doubt it is parallel, but the dipole moment is opposite to that of electric field E. Got it? So what happened when your dipole, let me tell you, your electric field is like this, your dipole will be lying here in this way, but what happened in this case, your dipole moment will be acting along this. That means your minus q will be on this side and plus q will be on this side, and your dipole moment is pointing from where to where, from negative charge to positive charge, right? This will be the direction of your dipole moment from right to left, and electric field E is from left to right. They are parallel no doubt, but opposite in direction, so we call it this as anti-parallel. Okay, so such anti-parallel condition, at that condition what happen, your U, that means potential energy, okay, that will be equal to PE. And when you compare all these different positions, different angles, what happen, this PE is maximum positive, and here your potential energy is minus PE, and this is the minimum. Now in that case, your dipole, okay, dipole, what happened, your dipole is acting what, if that electric field E is here in that first diagram, what happened, your dipole is lying like this, so that your dipole moment is in this direction. Got it? E is in this direction, so this is your electric field E, and this is your dipole moment P. Okay, let me draw like this. This is dipole moment from minus q to plus q. Now what happened, your dipole negative charge is experiencing a force against the electric field E, and it will be along this direction, right? Another force, this will be also acting, this positive charge will be experiencing QE in this direction, right, along the direction of the field. So two forces are experiencing, one against the field, another along the field, in the direction of field I mean. So the net force, total force, okay, this is one, another is toward the right side, another is toward the left side. So what happened, the net force will be equal to 0. So that means the force is balanced. Even though the net force is equal to 0, there is a rotating effect in this case. So what happened in this case, if that dipole is placed inside the electric field through some certain angle, then this dipole will try to rotate it. Okay, try to rotate. How? Because at some certain condition like this, net force is equal to 0, but torque is not equal to 0. Your tau is not equal to 0. That's why. What is this tau? Rotating effect of the force. That means your turning effect of that dipole is not equal to 0, and so it will try to rotate it. Up to what position this dipole will rotate? This dipole will try to rotate so as to have minimum energy. Every system in universe try to attain that least possible energy. Got it? So what happened? The least possible energy is in this case when theta is equal to 0. That means when this dipole moment will try to come with that of the direction of the electric field E. Got it? This dipole will try to rotate so as to align the dipole moment with the electric field E. In that case, we call it that as potential energy minimum, and it will be known as stable. Okay, why we call it as equilibrium? Stable equilibrium, because stable means it is possible only when potential energy is minimum. Equilibrium means what? Net force on it is equal to 0. Got it? That is why we call it as stable equilibrium. And in this condition, what happens? No doubt equilibrium will be always there. The net force is always equal to 0. But why it is called unstable? Because the potential energy at this angle, it is maximum. So we call it this as unstable equilibrium. Equilibrium, why? Net force is equal to 0. Unstable, why? Potential energy is maximum. Stable equilibrium, no doubt equilibrium, net force is equal to 0. Stable, why? This is a condition where the potential energy is minimum. So whenever there is what? Energy minimum, even though the net force is equal to 0, then we will call it that as stable equilibrium. Okay, unstable equilibrium when net force is equal to 0 and potential energy is maximum. Got it? And that is known as unstable equilibrium. So before winding up our class, let me give you one example. Okay, one very famous example for unstable and stable equilibrium. Now if you take a funnel, okay, if you take a funnel upside down like this, got it, upside down in this manner, okay, then what happened? In another case, what happened? You just take just like this the same funnel, okay, in this manner. No doubt you can place this funnel at the balanced position, right? At a fixed point like that, a particular point or at a particular position, this funnel can stand like this. But if you little bit disturb, then what happened? This will fall down. But at this condition, at this position, that one is the first one here, at this position, if you little bit disturb, then it will not fall down. That there lies a difference of these what stable and unstable equilibrium. Here in these two positions, okay, this will also be balanced. It will not fall down. You can keep it like this because this is a balance. You can also keep like this because this is also balanced. Net force acting on it in both cases are what? 0. Net force is 0. So it is what? Equilibrium, in equilibrium. But this one is stable equilibrium. Why? Because the energy possessed by it is what? Minimum. That's why when you little bit disturb from here, what happen? It will try to come its equilibrium position. But here in this case, when you little bit disturb the position, or if you little bit change, then what happen? This position will not be returning, rather this funnel will fall down, right? Why? Because the potential energy in this case is maximum. So this is a case for unstable equilibrium, and this is a case for what? Stable equilibrium. Likewise here also, in the case of stable equilibrium, suppose in that stable equilibrium your potential your potential energy is minimum, no doubt. This is direction of electric field, and if you take it dipole along this like this, minus q plus q here like this. If you little bit disturb, then it will try to come to this equilibrium position. Minus q on this side plus q on the right side, and this is your electric field E direction. Okay, and this is what your dipole moment in this direction. So what happen, as this energy is minimum, if you little bit try to tilt this dipole toward this, making pushing on this side, it will try to come to this equilibrium position. Why? Because potential energy is minimum, so it has not much the ability to do work, so it will try to come to its equilibrium position. But if it is in this position 180 degree, okay, dipole moment opposite to that of electric field E, angle between them is 180 degree. Okay, dipole moment and electric field E. So what happen if you little bit try to disturb this somewhere here? If you want to put a jerk, small jerk onto this positive charge or negative charge, then instead of coming to its equilibrium position like this, rather it will try to turn, okay, this dipole, so that its dipole moment is coming to this manner. Okay, dipole moment parallel to electric field E vector. So it has large amount of energy, so it has the ability to turn this dipole so that its dipole is coming from 180 degree to dipole moment 0 degree, I mean theta equal to 0 degree, like that. Okay, have you got this point about stable and unstable equilibrium? Yes, you must. Okay, with this we will try to come to the end of our today's class. Let's stop it here. Okay, thank you.